This presentation is delivered by the Stanford Center for Professional Development.
All right. I want to spend a little more time today on sampling theorem, sampling and interpolation, and some of the phenomena that are associated with it. I'll remind you what the setup was from last time. And I'll almost carry out the proof again, or at least I'll give you the setup for the proof again, because as I've said many times in this last time, and as I will say again today, for me, the sampling the derivation of the sampling theorem, the formula, is identical with the proof of the sampling formula. I think the two are so closely related that to understand one, you really have to think in terms of the other. All right? So here's the setup. We look at a signal which is band limited. That is to say, its Fourier transform is identically zero from a certain point on. All right, so suppose, say, f of t is a signal. F of t is a band limited signal. So I'll remind you again what that means. This was the key definition, really, that got the whole thing rolling. So that means that the Fourier transform, it's a condition on the signal. The Fourier transform is identically zero, say, for s bigger than or equal to some p over 2. I'm writing it, right? I'm writing it with respect to the order. And the smallest such p is called the bandwidth. There may be many p's for which that is true, but the smallest one is called the bandwidth. The smallest such p is called the bandwidth. Bandwidth is sort of a ubiquitous in signal processing, but I think this is, I don't know if this is the first definition of it, but I think this is the definition that's most commonly accepted. It's the smallest, you're assuming the Fourier transform is zero, identically zero from some point on, and the smallest number for which that's true is called the bandwidth. So the picture is this. Here's 0, here's minus p over 2, here's plus p over 2. And from there on out, going up to plus infinity, minus infinity, the Fourier transform is identically zero. Now, remember, you can't really plot the Fourier transform because the Fourier transform is complex. So, and the Fourier transform, if it's a real signal, is symmetric and all the rest of that jazz. So this is not to be taken literally as a picture, but it's something to keep in mind. That's sort of the general picture you should keep in mind. Next step, what is the clever key idea? You periodize the Fourier transform, FFS, by involving with that spacing. All right? That is, you look at this. The Fourier transform of f convolved with the Shaw function. And what that does is, because it's identically zero, outside going from p over 2 to infinity and minus p over 2 down to minus infinity, this just shifts it and adds it up, and you get a bunch of copies of the original signal, non-overlapping copies of the original signal. So here's 0, here is p, here is minus p, here is, again, p over 2. I'll get it out of the way in just a second. Here's minus p over 2, and so on, and so on. All right, so this is a picture of the periodized version of hello. Something wrong?
This one's cutting out.
This one's cutting out. It's okay. I wonder if it's because I dropped it. Okay. Back to live action. And then the main trick is to cut off. Then you cut off by the rectangle function of width p, and that gives you your original Fourier transform back. Cut off by multiplying by the rectangle function of width p. And that gives back the original Fourier transform because nothing is overlapping there, because you periodize and cut off. So again, the picture is like this, roughly. Here's 0, here's minus p over 2, here's plus p over 2. You multiply by the rectangle function of width 1. Remember, that's 1 between minus p over 2 to p over 2. So when you multiply, that doesn't do anything in that interval, and it sets everything to 0 outside that interval. So the result is the Fourier transform of f is equal to the rectangle function times the Fourier transform of f convolved with the Shaw function. This is the basic equation. Everything depends on this. It looks like, as I say, you've done something and then undone it, so how could it possibly lead to anything interesting, much less non-trivial? But it's the whole ball game, because now what you do is you take the inverse Fourier transform, and that swaps multiplication and convolution, and you have two instances of each here. You have an instance of each, I should say. It's multiplication here, so in the inverse Fourier transform, that's going to turn that multiplication into convolution. It's convolution in here. When you take the inverse Fourier transform, it's going to turn that into multiplication. Sampling comes from this part, and the sinc function comes from this part, and you turn the crank, and this is what you get. So you take the inverse Fourier transform and turn the crank. The inverse Fourier transform on the left-hand side is just a function again. The inverse Fourier transform on the right-hand side leads to the amazing formula. You get f of t is the sum from minus infinity to infinity f of k over p times the sinc of p t minus k over p. Okay, I managed to fit it all on the board. A little squeeze there, sorry. All right. The points k over p are the sample points. They're in the time domain, of course, are the sample points. And they're spaced 1 over p apart. All right? And what that formula does is it interpolates all values of the function in terms of the sample values. All right, you say, think of these as the values that you measure, say, and the question is, can you figure out what the values are in between in terms of the measured values, and under the assumptions and by virtue of the derivation? Yes, you can do that. All right. So the shifted sinc functions say sinc p t minus k over p. Sometimes you might call those the interpolating functions, something like that. Just let me just. All right, they're independent of the function f, all right? The only time f enters into the equation is through its sample value. So it interpolates all values of the function in terms of its sample values. It's a remarkable formula. It's an amazing formula, and it all depends on this, okay? That's why I say, and I will continue to say, that for me the sampling formula is identical with the derivation of the sampling formula. The reason why I say that, we'll see in a little bit, is because there are occasions when it goes wrong, or it's misapplied, or applied differently. And to understand that situation, you have to understand the derivation. Then, if you do, it's really quite straightforward. Okay, now there are a couple of there's some further terminology that's associated with this formula and with this whole circle of ideas. You also call the number p. So I'm calling it the bandwidth. That's an accepted term. You also call p when it's associated with a sampling formula like this. You call it the sampling rate. You call p the sampling rate. And you speak in terms of number of samples per second, or speak in terms of and because p has the units of frequency here, it's in hertz, so it's something per second. So usually speak in terms of samples per second. So you speak in terms of samples per second. All right? And again, if it's however many samples per second, that means the samples are spaced 1 over p, or whatever the rate is apart. And you also refer to the sampling rate for which the theorem is true as the Nyquist rate. That's also sometimes referred to. It's named after Harry Nyquist, god of sampling, who was one of the first to write this formula down in the context of telegraph signaling, I think, actually. So you also call p the Nyquist rate. All right. At least that's what I would call p. All right. But we really understand it again in terms of the bandwidth, and we understand it in terms of this formula. That's the most fundamental thing. All right. Now, of course, you can always sample at a rate higher than the bandwidth. All right. That's okay. Then your formula is still true. You can sample at a rate higher than p. All right. What does that mean in terms of your formula? Or what does it mean in terms of the derivation? it's still true so again, if here's the original Fourier transform, all right, going from minus p over 2 to p over 2, and if you sample at a rate, I don't know, p prime, bigger than that, then you are just periodizing to have period bigger than p prime. You can still cut off by that, and you're getting the original signal back. If you periodize by something like that, then you're getting something that is even has less overlap, so to speak. Looks like that. All right, and it's still true that if you cut off, you get the signal back again. All right, it's still true if you've cut off by the Fourier, by the corresponding rectangle function, you get the signal back again. You can turn all the crank. That's fine. You're doing more work than you have to. That means the sample points are spaced closer together. So it's still true. Go over here. Say all is okay, all is well with the rest of the derivation. You're getting more sample points than you need. The sample points are spaced closer together, and you're getting more of them, so to speak. So you're working harder than you need to. The sampling rate is higher, meaning the sampling points are spaced closer together. Now, the real question is, and I'll come back to it in just a minute, is what happens if you sample at too low a rate? But this is not an interesting question, so to speak. That is, nothing goes wrong. Everything is okay. The question is, what happens if you sample at too low a rate? All right, so we'll get back to this today. Before doing that, though, I have a couple of other comments, a couple of general comments about the formula. Let me write it down again. Actually, it's written up there, but let me write it again. Because there are some other interesting sort of natural phenomena that are associated with this formula. So I erased it, but let me write it again. So f of t is assuming that everything is all right. You've done the derivation. You know the bandwidth. You're expressing the function in terms of its sample points by this way. Now we start off sort of in a very physical context. We said, suppose you have a set of measurements and you want to fit the curve to the measurements. You want to fit a curve to the measurements. You want to pass through the points and so on. You will notice the sampling formula involves an infinite number of points here. Right? To interpolate the value of f by this formula involves a sum from minus infinity to infinity. They're a discrete set of points, a discrete set of measurements, but they're an infinite number of them. Interpolation depends on an infinite number of sample points. All right, so you might be quite disappointed in this, but that's the way it is. All right, so certainly for any practical application, you can only use a finite sum, and that will introduce an error. All right, so and that's another subject that we're not going to get into, but it's something to be aware of. So a finite sum, so you need a finite approximation. And there are results that tell you, that estimate the error and things like that. But again, these aren't things those are sort of in particular applications in particular contexts, and we're not going to talk about it, but just it is to be aware of. So in application, you'll need a finite sum. In any application, any real application. All right, so that introduces error. So it becomes an approximation instead of an equality, and that's something you have to be aware of. That's one thing. Okay? But actually, there's something deeper going on here. This is a deeper phenomena that's related to the fact you have an infinite number of samples here. And that is, well, let me state it as following. A signal cannot be both time limited and band limited. This is I'll write it, and then I'm not going to, well, let's discuss it a little bit. So the phenomenon is a signal cannot be both limited in time and in frequency. All right. Now, what that means is, what I mean by this is that there's actually two parts here. All right. If the Fourier transform is identically 0 for, say, s greater than or equal to p over 2, all right, so in the situation we've been dealing with, then f of t, well, the mathematical way of saying this is does not have compact support means that it is not identically 0 at some point, all right? It is not identically 0 for t sufficiently large. All right? So if it's limited in time, if it's limited in frequency, it cannot be limited in time. I'll give you an argument for this in just a second, but let me just state the facts now. So once again, if it's a sequence cannot be limited in frequency and limited in time. If it's limited in frequency, it cannot be limited in time. And conversely, the same thing holds switching the two domains. That is, if it's limited in time, it cannot be limited in frequency. So likewise, if f of t is identically 0, say for t, I don't know, bigger than q over 2, something like that, you know, just outside some range, then the Fourier transform of f of s is not identically 0. It does not have compact support. It can't be identically 0 for s sufficiently large. All right. You can go back and forth between the time domain and the frequency domain by Fourier transform. You have the same property or the related properties here in either domain. All right, so that in the context over here, because we're assuming the signal is limited in frequency, it can't be limited in time. So you shouldn't expect to be able to interpolate it with only a finite number of sample points. All right? A finite number of sample points would only go out so far on the graph, but the graph goes on forever. All right? You can't expect to interpolate values way out on the graph by only staying to part of the graph. Yeah?
As opposed to just bounded?
Sorry?
Of the Fourier transform. Is there a reason you say compact support, not just bounded support?
I say compact. Compact is sort of the technical term for it. It means closed and bounded. So it means it's zero outside some closed interval. That's just for a mathematical term. So you could think of it as, I mean, I just find myself using that terminology because it's fairly standard. It's certainly standard in math, and you see it more and more in the engineering literature, but don't sweat it so much. Compact means closed and bounded. So outside a compact interval means outside some closed and bounded interval. Okay, closed meaning it includes the endpoints. There are technical reasons why you have to include that, why you have to include the endpoints when you talk about things like that. All right, so once again, let me just to emphasize why this has to be the way it is, why it involves an infinite number of sample points. If it's a finite extent if it's a compact support in the frequency domain, if it's band limited, that means it cannot be time limited. So the signal has to go on forever, and you can't expect to interpolate way out in the tails of the signal by only a finite number of points. All right, so it should involve an infinite number of sample points. That's just the way it is. All right, given these results. Now, why is this true? Well, I'll give you a sort of a somewhat bogus argument. There's a more precise argument that's given, more rigorous argument that's given in the notes. So let me prove this, that if the Fourier transform of f of s is identically 0, for, say, s bigger than or equal to p over 2, then f of t goes on forever. Forever. All right. The reason why this is true is, and it's sort of analogous to what we did in actually deriving the sampling formula, although with one exception. Since the Fourier transform is 0 after a certain point, again, here's minus p over 2 to p over 2. Here's the Fourier transform. Then it's equal to its cutoff. The Fourier transform of f, if I cut off by multiplying by a rectangle function of that width, I haven't changed anything because the rectangle function again is 1 between minus p over 2 and p over 2. If I scale it by p and 0 outside it, so I haven't changed anything. Now take the inverse Fourier transform on both sides. I haven't periodized here. Right? This is a different argument. I'm not deriving the sampling formula. I'm proving this statement. If the Fourier transform is identically 0 from a certain point on, then f of t goes on forever. Why is that? Well, write this statement out and then take the inverse Fourier transform. So again, it looks like I haven't done anything here because I've just written the Fourier transform in terms of the Fourier transform. You know, I haven't done anything. But now if you take the inverse Fourier transform, the miracle that happens is it swaps convolution and multiplication. All right? So if I take the inverse Fourier transform, you get f of t is equal to the inverse Fourier transform of this, which is a scaled sinc function, sinc pt, convolved with f. All right? Sort of a striking statement, actually. All right? It says that for these functions, the sinc function is, in some sense, functioning like the delta function or functioning like an identity for convolution. All right? The sinc function won't do that for all signals, but it will do that for the band-limited signals. All right? So f is the sinc convolved with f if the Fourier transform of f is 0 beyond a certain point. Now, here's where I'm just going to wave my hands. I'm going to say what this means is, and I think you can probably make this precise, although there are actually better arguments for the whole circle of ideas, is that the sinc function goes on forever. All right? So convolving f of t, whatever happens with f of t with a sinc function, is going to stretch out f, is going to smear out f so it goes on forever. It's never identically 0 beyond a certain point. And so f is never identically 0 beyond a certain point. It's a strange looking equation, I understand. But the way to sort of, the conclusion that you draw is you're convolving f with a sinc function, just looking at the right-hand side. This function on the right-hand side, you would say goes on forever. Is not identically 0 beyond a certain point. And what do you know? It's equal to f. Okay? So the right-hand side goes on forever. All right. I don't know if you can actually make this argument completely rigorous. It's the one that's always given in electrical engineering classes. I don't like it myself, but it sort of gives you some reason for why this is true. And as I say, there's actually a more rigorous argument that's given in the notes, but I won't go through that. Okay. But nevertheless, it's an important principle. All right. Now, this is an example. You gotta think about this a little bit. In some sense, this is an example of where mathematics meets the real world and they disagree. All right? You know, we think about mathematics as giving a pretty accurate description of the real world, and it's kind of spooky sometimes how well it works. But in the real world, signals really don't go on forever. Real signals really don't go on forever. And in the real world, signals really are limited in frequency. The frequencies don't go on forever. All right? This says that you can't have both of those. All right? You cannot have a signal which is both limited mathematically. You cannot have a signal which is both limited in frequency and limited in time. It can't be. If it's limited in frequency, it's unlimited in time. If it's limited in time, it's unlimited in frequency. All right? But any real signal is limited in time and limited in frequency. So there's a clash. All right? There's a clash between the mathematical description, between the mathematical theorem, and what you actually encounter. Okay, I mean, that's something to take note of. All right? On the other hand, so that's just, to say mathematical models are imperfect or the real world is imperfect, however you want to look at it. Okay? On the other hand, you can also look at this in some way as like a qualitative version of the uncertainty principle. And we've seen situations somewhat like this before. That is, we've seen, remember, concentrated in the time domain means spread out in the frequency domain, or concentrated in the frequency domain means spread out in the time domain. And we've seen various instances of that, and that's a very important principle in Fourier analysis. It's very important for your intuition that realize that if something is concentrated in one domain, it's spread out in the other domain. So here, concentration is in terms of compact support. If it's identically 0 beyond a certain point, it has to go on forever in the other domain. All right? The uncertainty principle in quantum mechanics, is a statement about you can't simultaneously localize two physical quantities, momentum and position, say. Right? And that's also was sort of a shock to people's conception of the physical world and how mathematics model the physical world. I mean, the idea is you should be able to localize with arbitrary precision both where something is and how fast it's going. All right? But, from the point of view of quantum mechanics, that's not true. You can't do that. And this, in some sense, is maybe can viewed as related to that. All right? So, maybe it's not a mathematical imperfection with the way the real world is. Maybe you have to change your mind the way the real world is. Maybe you're making an imperfect statement. When you say a real signal cannot be limited in time and it has to be both limited in time and limited in frequency. Maybe that's really, also an approximation. All right? So think about that tonight, as you're lying in bed, staring up into the abyss. Okay. There is, by the way, we didn't do it, but But there is in the notes actually also a proof of the uncertainty principle, a precise proof of the uncertainty principle, which does talk about exactly, and there are various ways of formulating it. It's the sort of the support of the function and the support of the Fourier transform, where the Fourier transform is non-zero, where the function is non-zero, and and relates those two in a more quantitative way. This is sort of a qualitative statement: is that it can't be both both concentrated in time and concentrated in space, or it can't be both time limited and band limited. But there are ways of making these statements more quantitative. They're interesting, and they're interesting. Okay, now. I'm sure I didn't miss any more profound statements here. Okay. The final thing I want to talk about, I think I told you, I love this material. I think the sampling theorem and all the material surrounding it is really fascinating. But, if I had my way, I just do it more and more. Talk about it more and more. But I really only want to talk in a little bit more detail about one other phenomenon that's associated with sampling and interpolation, and that's the phenomenon of aliasing. That's you sort of think of as the natural phenomenon associated with a misapplication of the sampling theorem or misapplication of the proof. So aliasing and interpolation, two. Aliasing and interpolation is the other comment that I want to, the other sort of circle of ideas that I want to talk about. All right, so one more time, the fundamental equation is f of t is band limited. The Fourier transform of f of s is identically 0 for s greater than or equal to p over 2. And you have the equation that the Fourier transform is the cutoff of its periodized version. All right? Everything depends on that. Everything depends on that equation. Okay, now, here's a common problem for signals that you might want to interpolate, for signals that you're sampling. If you know the bandwidth, if you know p, or you have a pretty good idea of p, and you can always take p too large. All right, that's not a problem. You're working harder than you have to, but at least as far as this formula goes, it's okay if you're beyond, it's okay if you take a p beyond where the Fourier transform is identically 0. The problem is if you don't know the bandwidth so well and you take a p that's too small. So what happens if you try this for a, let's call it p prime that's too small? Okay? All right. So here's the picture. It's band limited, all right, so there's a real value for the bandwidth, but you take something that's a little bit too small. Here's p minus p prime over 2, here's plus p prime over 2, and actually the Fourier transform bleeds out a little bit over that. Okay? All right, you can form the periodization. You can derive the sampling formula just like you always derive the sampling formula. Right, you can form the Fourier transform of f convolved with p prime, with a Shaw function with spacing p prime, and you can cut it off. What do you do if you what do you get if you form that? Well, if you form that, again, here's the Fourier transform with his real bandwidth shown. If I periodize with less of a period, with too small a period, minus p prime over 2, p prime over 2, then what's going to happen is if I shift it by p, prime, then I'm going to be getting, it's not going to be shifted off itself. It's going to overlap. All right? It's going to overlap and add up. So it's not only overlapping, but the sum of, so this new function, the Fourier transform of f convolved with a Shaw function which is spaced a little too close together, is going to give you something that looks like this. And so on and so on. Now you should convince yourself of that. All right, it's not hard to see pictorially what's going on, and that's exactly what the issue is. And you can but anyway, you can do it. That's fine. And you can also cut off. All right, then you can cut off. You persevere here. You can cut off by, you think you're doing everything right. All right, you think you're doing everything fine. So you cut off by that. You form pi p prime times the Fourier transform of f convolved with the Shaw function of p prime. All right? Now, what you get is, if you cut off by the corresponding, let me see if I can draw the picture here again. It's roughly like this. I'll just try doing two things. So the picture is something like, here's b prime, here's the new curve by the sum. This goes like that. All right, if you cut off by the rectangle function, then the curve you get is this, right? That's not the original Fourier transform. You don't get back the Fourier transform of f. Okay? You don't. But you persevere. You don't know that, right? You are a Stanford engineer. No mistake will stop you, right? All right? You persevere. What do I mean by persevere? You take the inverse Fourier transform. You derive the sampling formula, all right? Because the sampling formula is identical with the derivation of the sampling formula. All right? So you take the Fourier transform, inverse Fourier transform of this. Pi p prime, Fourier transform of f convolved with Shaw function of p prime, just as you always did. All right? And what do you get? You get a sampling formula. You get the same formula that looked like you had before. You get the sum from minus infinity to infinity, the value of f at these sample points, k over p prime, times the shifted sinc function, sinc of p prime t minus k over p prime. That's what you get. You take the inverse Fourier transform of this expression over here, you turn the crank, and that's exactly what happens. But you don't get f. You can't get f. All right? You can't get f because this is not the Fourier transform of f. You get something, but you don't get f. You do not get f. You do not get f of t because the derivation of the sampling formula is identical with the proof of the sampling formula, and you don't have this. You have, because the Fourier transform of f is not equal to the cutoff of its periodized version. Because the Fourier transform is not recovered this way, that formula can't be recovering f. Can't be. All right, you don't get f, but you get something. What do you get? Okay, what is the relationship between what you get? What do you get? Well, let's call it, so everybody got this? This is a very important point. All right, let's call it G. You get something. It's a fine signal. So call this G. So let's say G of t is this sum. K equals minus infinity to infinity f of k over p prime, sinc of p t minus k over p prime. That's it. Okay? What does G have to do with f? Anything to do with f? Yes. It has the same sample values of f. F and G agree at the sample values. So f of t and g of t agree, are equal at the sample values. K over p prime. Why? Because g of, let's take one, so g of m over p prime. All right, that's a sample value for some value of m. All right. So what is that? That's the sum, k going from minus infinity to infinity, f of k over p prime, sinc of p, m over p prime, minus k over p prime. Right? Now look at what's happening in the sinc function there. In the sinc function, the sinc of p, m over p prime minus k over p prime. You have to remember some properties of the sinc function here. Multiply the p through. So that's sinc of m minus k. Right? That p prime's in the denominator in both cases. The sinc function, this is a sinc function in an integer. M and n or m and k are integers here. All right? It's 1 when m is equal to k and 0 otherwise. All right? This is equal to 1 if m is equal to k and 0 if m is different from k. And the sinc has 0 crossings, if you want to think of it that way, use that terminology, at the integers. All right? Except at the origin where it's 1, where it's equal to 1. All right? So all these terms drop out except when k is equal to m. In other words, to write it down one more time, g of m over p prime is equal to this sum, k going from minus infinity to infinity, f of k over p prime, sinc p, m over p prime, minus k over p prime. All the terms drop out except when when k is equal to m, and that then gives you f of m over p prime. All right? They agree at the sample points, but not elsewhere. There may be some other accidental agreement. Who knows? Who cares? But the one thing you do know is they agree at the sample points. All right? Because of this property, you say that G is an alias of F. Or that F and G are aliases of each other. I don't know which way. So you say that G of t is an alias of f of t. It's not equal to f of t, but it has the same sample values as f of t. Now what that means is, among other things, if you know only the sample values, if that's all you know about f, you cannot distinguish f from g. All right? You know some things about f, say. You know the sample values. You make a guess about the bandwidth. All right? If you guess wrong and you reconstruct g according to the derivation of the sampling formula, because the sampling formula is identical with the derivation of the sampling formula, then you are constructing not f, but an alias of f. But you don't know that. All right? You don't know that because you don't know anything about f other than its sample values. Sorry, you cannot distinguish the two. That's why I use the term alias. You know, it's a perfect masquerade. All right? It's g masquerading as f because they have the same sample values. Okay? And it arises, I wouldn't say not from the misapplication of the sampling formula. I don't think that's fair. It follows from deriving the sampling formula as you would ordinarily when it doesn't apply, or rather when you don't get back, when that fundamental equation relating the Fourier transform, the periodized Fourier transform, is not valid, is not satisfied. You get something, you know, you can turn the crank, you get a formula, but you're not reproducing the original function. Now, you've probably studied aliasing and things like that, and not today, but I hope next time actually I'll bring in a demo of this. And you may have talked about various things, folding in higher frequencies to lower frequencies and all the rest of that stuff. That's fine. But for me, again, I never think of the sampling formula without thinking of the derivation of the sampling formula. And if I want to understand aliasing and what's going on in aliasing, I think about exactly this argument. What's gone wrong? Or what are you doing? The derivation was fine. Everything we did was fine. But what's not true is this fundamental equation. You have the Fourier transform is not equal to the cutoff of the periodized Fourier transform. I called it P prime here, all right? If the Fourier transform is not equal to the cutoff of the periodized Fourier transform, then what you're getting back by turning the crank, by writing down the sampling formula, is not reproducing f. It's reproducing something else. It's reproducing an alias of f. Okay? Now, I want to show you one explicit example. This is a fairly simple example, but a nice one. And this is done in the notes, actually. All right, so I won't go through all the details, but I want you to see how it works in one particular case. So again, you know, I want to stress this, that in aliasing, it's not that you've done something wrong. You know, you have reproduced a signal that has the right sample values, but it's not the signal that you hope to reproduce because of this. Because of this. All right? It's not that you made a mistake somehow, or maybe you have made a mistake, but you know, you haven't sinned against the forces of good. You know, it's just that you're deriving the sampling formula, you're pursuing the argument the natural way of pursuing it, but you're not getting back the original function because this equation is not satisfied. Okay? So I want to do an example. So again, this is in the notes. Example of aliasing. All right, so I'm going to take just a cosine. So the spectrum is just two delta functions. F of t is the cosine of 9 pi over 2 times t. All right, so it says frequency 9/4 Hertz. And we know what the Fourier transform looks like. The Fourier transform of f looks like two delta functions. Looks like 1/2 delta s plus 9/4 plus delta s minus 9/4. All right? So, what's the picture? The picture is this. The picture is, here's the Fourier transform. Here's 0. There's a delta at 9/4. There's a delta at minus 9/4. Now, a little tricky here, and this is something that, again, is discussed in the notes that I'm going to sort of skate over now. How would you, now, so you want to reproduce this function by a sampling formula somehow, all right? So what do? You periodize this, you cut off, and so on. So how would you periodize this? What is the appropriate p to take? Well, the appropriate p to take should be anything strictly bigger than 9/4 because you want to shift this completely off itself. The problem here is that there's a spike right at the endpoint, all right, and it drops sharply. All right, so there's a little bit of an issue here at the endpoints, but let me just say sort of skate by that, and you can look at the notes on that for a little bit more detail. So the proper sampling rate would be anything greater than 9/4 because convolving this thing by a Shaw function with that spacing, anything bigger than actually 9/2, twice this, right? The whole bandwidth would be okay. All right, so you would want to convolve. So p here, p over 2 is 9/4, so p is equal to 9/2. But again, you want to take p anything bigger than that to get to shift the spectrum off itself. To shift the spectrum off itself. Convolving with the Shaw function of spacing p. All right. Again, there's a little bit some more to say here at the endpoints, but never mind that right now. The phenomena that I want to talk about is what if you can't do that? What if your sampler is stuck in low and you sample at too low a rate? All right. So what if we can't do this? What if the sampler is stuck in low? All right. So for example, e.g. sample at rate p is equal to 1. Okay, so in order to reproduce this thing, you'd want to take samples at a rate greater than 9/2 Hertz, but you can't only do that. You can only take samples at a rate of 1 per second. All right, play along. The sampling formula is identical with the derivation of the sampling formula. What do I have to do? To sample at a rate 1 means to convolve with Shaw sub 1. Sorry, probably should have said that a little bit more forcefully when I was talking about the original derivation. To sample at a rate p means to convolve with the Shaw function of spacing p. To sample at a rate 1 means to convolve with the Shaw function of spacing 1. All right? To sample at p equals 1 means to form the cutoff and the periodization and the cutoff. Means to form pi 1 of the Fourier transform of f convolved with the Shaw function of spacing 1. Period. All right, that's what it means. Because the sampling formula is identical with the derivation of the sampling formula. Now, all right, you can form, and I won't do it, you can easily form that convolution, 1/2 delta s plus 9/4 plus delta s minus 9/4 convolved with the Shaw function, k equals minus infinity to infinity, delta of x minus k, spacing 1, all right? All you use is, I'll remind you of a formula for convolving delta functions, shifted delta functions. You use delta a convolved with delta b is delta a plus b, okay? All right? And you find if you do that, you get a bunch of arrows, all right? You get a bunch of arrows, but you find only that 2 of them lie within them. I mean, there are 2 parts of the derivation of the sampling formula. There's periodizing and there's cutting off. All right? So you get a bunch of arrows, but then you have to ask yourself, this is pi 1, which arrows are within the interval from -1/2 to 1/2? So only 2 arrows, only 2 deltas within -1/2 less than s less than 1/2. That is, what you find is, you find that, where is it here? You find, I want to be sure I got this right. You find only, matter of fact, at 1/4 and -1/4. Only s equals, only delta s minus 1/4 and delta s plus 1/4. That is to say, if I take the if I cut off by a rectangle function of width 1, the Fourier transform of f convolved with a Shaw function of spacing 1, the only thing that remains are these 2 delta functions. That is, it's 1/2 delta s plus 1/4 plus delta s minus 1/4. All the other deltas are outside the range. Okay? All the other deltas are outside the range. You just check that out algebraically just by convolving using this formula. Okay? All right. Play along. What does the derivation of the sampling formula say? The derivation of the sampling formula says take this formula and take its inverse Fourier transform. Derivation of the formula says to take the inverse Fourier transform of pi 1 of Fourier transform of f convolved with pi 1. That'll give you the function. That'll give you the so-called interpolating function. So what do you get? You get the inverse Fourier transform of that. That's easy. That's a cosine. That's another cosine. This is the inverse Fourier transform of 1/2 delta s plus 1/4 plus delta s minus 1/4, and that is the cosine of pi over 2 times t. All right? Deriving the sampling formula at the sampling rate 1, which is too small, has led to the function cosine of pi over 2t, not to the function cosine of 9 pi over 2 times t. All right, deriving the sampling formula, once again, leads to the function g of t is cosine of pi over 2 times t, not to f of t is equal to cosine of 9 pi over 2 times t. All right, it's not that you've done something wrong. You haven't made any mistakes along the way, other than the mistake of taking too low a sampling rate. But you've turned the crank, and you found a function. But you didn't find the function you wanted. All right. But you did find a function which agrees with the function that you wanted at all the sample values. And you find that g of t equals f of t at the sample values, at Which sample values? The sample values corresponding to taking samples every second at 0, plus or minus 1, plus or minus 2, and so on and so on. Okay? You have found an alias of the function, not the function. You've done that by deriving the sampling formula with a sampling rate that's too small. All right? In the sense that the fundamental equation, the cutoff of the periodized Fourier transform, does not give you the Fourier transform back. All right? That fundamental equation is not satisfied. All right? And so what you've come up with is something different. Okay? That's the main. This is sort of the natural phenomenon that's associated. Aliasing is, so to speak, the natural phenomenon that's associated with the sampling theorem. All right? But it is nothing other than doing the right work sort of in the wrong cause, so to speak, all right, by taking the wrong sampling rate, by taking a sampling rate such that the fundamental equation is not satisfied. Okay? All right, that's all about I wanted to say on this, actually, as much as I love this topic. So next time, actually, we're going to use it to give a derivation of the discrete Fourier transform, and we're going to move into the modern world from the analog to the digital. All right, next time.